This is the video for section 11.5 on alternating series. And these are the series where, unlike in the previous sections where we had all positive terms, these are the ones where the terms alternate sign. So for example, we could consider the sum 1 over root 2 minus 1 over root 3 plus 1 over root 4 minus 1 over root 5, etc. That's an alternating series. Because the signs flip back and forth between minus, plus, minus, plus. And one can rewrite this series as the sum n equals 1 to infinity of minus 1 to the n minus 1 times 1 over the square root of n plus 1. Right? And the way that we see that is the sums, since the signs of the terms are alternating, we have to identify which of the signs, the powers of negative 1, correspond to the signs that are occurring up here, plus, minus, and then to evaluate the pattern that occurs in the numerators and denominators that we might see. Now, alternating series are, in some senses, much nicer than the positive series that we dealt with earlier. There's a very nice test for the alternating series, and it's called the alternating series test. And so you start with a series that looks like the one we had above, so it's the sum n equals 1 to infinity, negative 1 to the n minus 1 times bn, where those bn's are going to be strictly positive. Okay, so this is exactly indicating that the sum we have, the sign is all inside the powers of negative 1, and those powers are going back and forth, plus, minus, plus, minus. Now, if you have a series that looks like that, and we assume that that sequence of positive terms, bn, is non-increasing, and that just means that when I go from bn to bn plus 1, that bn is always greater than or equal to bn plus 1, and that's true for all n, and that the limit as n goes to infinity of the bn is 0. Right? So notice that this last condition implies that the original series that we're looking at up here has its nth term limit equaling 0. And previously we said that we can't draw any conclusions using the test for divergence, and that's absolutely true. But because we have an alternating series and we have this non-increasing pattern with the limit equals 0, that the conclusion that we get to draw is that this series actually converges. So this is a very strong test for convergence of alternating series. Now I want to reiterate this. This test only works for alternating series. And so on the next page we will talk about this for a specific example. So I want us to look at the example summation n equals 1 to infinity, negative 1 to the n minus 1 times 1 over square root of n plus 1 that we considered before. And I claim that this converges by the alternating series test. And that's true. To check that that's true, we need to check three things. So where we have Bn in this case is 1 over the square root of n plus 1. I need that to be positive. That's always true. We need it to be non-increasing. And for that we need to know that 1 over the square root of n plus 1 is greater than or equal to, this is the thing that we want to check, 1 over the square root of n plus 2, right? So that when so let me rewrite this in a slightly different way. What we're checking is that 1 over square root of n plus 1, that's our Bn, is greater than or equal to our Bn plus 1, which is 1 over square root of n plus 1 plus 1. Right? And that's the thing that we have to check in this particular case. And that's true because n plus 1 is less than n plus 2. So the denominator that I have on the left, so I have smaller denominator, which leads to a larger quotient. You can also check this if you want using an alternative technique of checking the derivative. So you can check that that function is decreasing by showing that its derivative is negative, and that will tell you that the sequence of terms that we're looking at, the Bn's, are non-increasing. So that's the second thing we need to check, right? So we checked the positive terms up here. We checked that the sequence of Bn's is non-increasing. And the last thing we need to check is that the limit as n goes to infinity of Bn equals 0. Right? That's the last thing, and then we get to apply the alternating series test in order to conclude that the series converges. And this one, checking that this limit is 0, so that's the limit of 1 over square root of n plus 1, and we know that the function 1 over square root of x plus 1, that definitely equals 0. Right? That graph looks something like this. For more examples like that previous one, you should look in the book, see examples 1 through 3 in the text. So the next thing that we're interested in doing for these is to estimate the alternating series using partial sums. So for this I'm going to write the partial sum Sn as the sum k equals 1 to n minus 1 to the k minus 1 bk, right? And just like before, we did this with the integral test. We're going to write r sub n equal to s minus sn, and so that's the difference between the series k equals 1 to infinity, negative 1 to the k minus 1 times bk minus that nth partial sum that I wrote there. And it's a fact. So if we assume again that the bk's are all positive and non-increasing, just like in the alternating series test, and such that the limit as k goes to infinity of the bk's is 0, right? So make all the assumptions that you made for the alternating series test, and then it is a fact that the absolute value of the error from that estimate of the alternating series by using the nth partial sum is less than or equal to bn plus 1, the n plus first term. Okay? And so I want to show us how we use that in a particular example on the next page. So for example, I want us to consider the series that we had previously, k equals 1 to infinity minus 1 to the k minus 1 of 1 over the square root of k plus 1. I'm writing in terms of k's instead of n's, but the test is applied exactly the same way. So we want to find a value for n so that Sn is correct approximation of that series, let's call it S, to 3 decimal places. So it's correct to 3 decimal places. Right? And so note, we have already checked that the hypotheses of the alternating series test hold. So we have that the bn's are all positive and non-increasing, and the limit as n goes to infinity of the bn's is 0. Those are things that we have already checked and confirmed, so we won't do that again. And now what we'll do is we'll say what we need is to find n so that bn plus 1 is less than 0.001. In other words, less than 10 to the minus 3. That's what it means to be correct to 10 decimal places. And so that's saying that we need 1 over the square root of n plus 2 to be less than 10 to the minus 3. And if I take reciprocals and square both sides, so reciprocals say that we need square root of n plus 2 to be greater than 10 to the 3. That is, we need n plus 2 to be greater than 10 to the 6. Right? So here I took reciprocals, and here I squared both sides. Okay? And so that means that we need n to be any number that's greater than 10 to the 6 minus 2. And that's, right, if I actually asked you to use that number to estimate the series, you would have to add up 10 to the 6 many numbers, and that's a lot of numbers. So for this particular example, it's not necessarily a practical number, but The point is, you don't have to do any additional work in order to know that this estimation that you used is actually accurate to the correct number of decimal places. All right, so that's the end of the lecture on section 11.5.